Hello, everyone. My name is Jolie Yu, and I am a Customer Success Engineer at Comsof. I would like to welcome you to our webinar today, where we will discuss combined 5G wireless and wireline planning, a collaboration between Comsof and Siradel. Today, we will learn about the advantages of an integrated 5G fiber design solution, how this will save you both time and money in brownfield and greenfield scenarios, and then we will show you this turnkey platform in action. For those of you who aren't familiar with our companies, Comsof Fiber is the leading software for automating and optimizing the design of fiber networks. Siradel produces 3D digital twins of cities and 3D simulation and visualization software solutions applied to the design of 5G and smart city infrastructure. If you'd like to know more, please visit our website. Now I'd like to introduce you to today's speakers. From Comsof, we have Kevin Nguyen, and from Siradel, we have Sylvain Guivarch. I will now hand this over to Kevin.
Thank you, Jolie. We appreciate everyone who is joining us for today's webinar. As Jolie mentioned, today we are going to look at a unique integrated approach to planning and designing 5G networks. Now, 5G networks come with new deployment challenges in terms of wireless site density and front haul capacity. However, if the planning methodology used for these networks remains unchanged from previous generations, the opportunity for performance and cost optimization will be missed. Both Comsof and Siradel have been involved in fixed wireless and early stage 5G mobility network designs, and from this experience, we have seen the need in the market for a turnkey offering. Today, we will examine why an integrated wireless and wireline solution is so powerful. We'll delve a little deeper into how both the Comsof and Siradel solution works, and look at two specific use cases for the software, and finally even see a little demo of the integrated solution. So before we start discussing how to utilize an integrated planning approach, it is worthwhile to quickly touch on 5G and its need for fiber. In the coming years, the anticipated increase in mobile consumer demand is shaping the development of broadband services. This demand, in addition to the use cases such as enhanced mobile broadband, massive machine-type communications, and ultra-reliable low-latency communications, are all driving 5G, the fifth generation of mobile networks. 5G will require many evolutions in the network, such as massive MIMO, network slicing, and C-RAN. While all of these are important, they're not the topics we're going to be talking about today. The two aspects that are most relevant to today's discussion is the densification of the cell sites and the requirement for fiber to these cell sites. The high bandwidth, high speed, and low latency requirements of 5G means that wireline, specifically fiber, will be required for the connectivity of antennas, or more precisely, small cells. In order to achieve the performance requirements, it will also require the densification of our cell sites as close to a couple hundred meters in urban areas. It is this combination of requiring fiber and having a large quantity of wireless sites that provides us with a huge opportunity for savings with a combined planning approach. So now let's first look at the traditional wireless network design process that we so often see being utilized. It is an isolated and siloed approach, with each group acting almost in a vacuum and optimizing for their own requirements. With regards to the workflow, we see the antenna or small cell locations being determined first. While we would like to believe these sites are based on the results of wireless modeling, it is often just the result of placing them on a map. Once these sites are determined, the locations are then passed on to the wireline group, who determines how to connect the sites to their network. Clearly, this is not an optimal workflow, as we are not considering the wireline, specifically fiber, when selecting our antenna locations. Now, this may have been acceptable in the third or fourth generation mobile networks, when there were less sites and more wireless backhaul. However, it is not sufficient for 5G design. So, how do we do this? How do we consider all of the wireless performance and cost variables in the network design? More importantly, how do we optimize our design for these wireless considerations while also considering all of the fiber or wireline components. The answer is with a joint integrated solution that is able to consider your fiber assets while placing your wireless sites. So how does it work? Well, at a very high level, without getting into the weeds, it looks like this. The user first specifies their 5G coverage parameters. This can be things such as frequency, bandwidth, and all the possible candidate sites. We then identify multiple sets of candidate sites that meet these performance requirements. Then we optimize the fiber for all of these different sets of candidate sites. And then we identify the least cost result and design that as our network. This is essentially an optimized global infrastructure for our 5G design. So before we actually look at the solution and use cases, it's important that we understand how each of these two softwares work. So Comsof Fiber is a GIS-based software that automates the design of fiber networks. It can be any type of fiber network, whether fiber to the home or the fiber required for a 5G network. It utilizes GIS data in combination with a set of design rules which specifies your architecture, cables utilized, aerial versus underground, and the material and labor costs for all these components. It then optimizes your equipment placement, routing, and selection of all the components required to build that fiber network. I'll now hand it over to Sylvain, who's going to explain Siradel and look at our first use case.
So thanks, Kevin. A few words about S5G Connect. S5G Connect is Siradel RF planning tool dedicated to the design of wireless access, fixed or mobility, as well as the design of wireless backhaul networks. In S5G Connect, the user defines the characteristics of the wireless network he wants to design, radio, the technology, the frequency bands, and the topology, and then run 2D or 3D network analysis like the one you see in the slide here, and we're generating those simulations with a ray tracing propagation model. One of the features of interest today is the automatic design capability that allows the user to automatically position cells to reach wireless coverage targets. That's the feature that has been interfaced with Comsof tools and that we'll be presenting and demo today in the next slides. So during this webinar, we'll be presenting two use cases describing a joint wireless fiber design approach. The first use case describes a scenario of joint 5G millimeter wave access and fiber backhaul design, where we will demonstrate the value of the joint design and compare it with a sequential design approach where the two designs are done separately. The second use case is an analysis of fiber network deployment supporting both 5G and FTTH, and we'll be analyzing cost savings achieved with a unified design approach. So for the first use case, the joint wireless access and backhaul design, we have defined an area of 4 square kilometers in downtown San Francisco with a mix of a dense urban and an urban environment. The antenna that we are deploying here are millimeter wave small cells located on lampposts, and in this use case, all the small cells will be backhauled with fiber connectivity. The study here is on mobile broadband coverage, but the same approach that we are describing here can apply to fixed wireless access. The objective of the design is to reach the coverage target that we will set as an input of the study, and we will combine this objective with another one, which is to minimize the overall cost of the network. So to achieve this objective, we are demonstrating here the value of a joint approach that combines wireless access and fiber design, and the results we're achieving here will be compared with a sequential design where the two designs are done separately. So regarding the assumptions that we're considering for this first use case, as mentioned before, the small cells will be deployed on lampposts. So for that, we're using a database of lampposts in the study area of about 4,000 locations of lampposts. It's on the left picture. Then on the wireless link budget table, we're defining the characteristics of the antenna that we'll be deploying. So that has been configured to simulate the coverage of a 28 gigahertz network with beamforming antenna. And the objective here is to cover 80% of the study area for an in-street receiver. Then the bill of materials table summarize the costs that are considered for this analysis for additional fiber and additional small cell deployments. Two similar but different scenarios are analyzed here to avoid looking at a specific scenario. They are sharing similar characteristics in terms of existing fiber asset, like similar lengths, for instance, for pipes and cables sharing the same central office, but they have a different geographical distribution. So in this slide, we are presenting the results of the joint design combining Siradel and Comsof tools. On the wireless access side, 83 small cells have been selected out of the 4,000 candidates, and fiber has been deployed to provide backhaul connectivity to the 5G small cells. And you can visualize the results with the picture on the left with the location of the small cells. On the right side of the slide, the cost of the network is analyzed by taking into account the deployment of the antenna as well as the cost to deploy fiber to the antenna. And this is divided into three main categories. The same results have been also generated and presented here for the second scenario. We are achieving the same number of small cells deployed over the area with different locations, and the total cost of the network is also slightly different due to the slight variations of the inputs for this analysis. We're now analyzing comparative charts between the sequential and the joint approach. In the sequential approach, the two designs, the wireless and the backhaul, are done separately, and the joint design, both the wireless and the fiber design, are done at the same time. What we can see is that with the sequential approach, a lower number of small cells, 76, are required to reach the design objectives on the two scenarios. However, the cost of the overall network is higher. It is more expensive to bring fiber to some of those locations, which make the design less efficient. So we're observing the same trend for the two scenarios that have been analyzed here. And overall, in this use case, what we can demonstrate is a total network cost reduction of about 22% achieved with the joint approach combining the two tools.
So in this video, we're showing how Siradel and Comsof tools are interfaced to run the scenario we have seen in use case 1. The first step is to import 3D GIS data that will be leveraged for propagation computations as well as the design of the fiber networks. The 3D GIS data includes building and footage polygons that are critical in this scenario for the millimeter wave propagation simulations. Then in the project, we have imported other information for this use case, the location of the central office here, as well as the location of the study area. So a dense urban area in San Francisco, as well as an urban area visualized here. We also imported other information about the existing cables, existing pipes, as well as the existing point of presence in the area. And also imported the location of the site candidates that will be used to automate our design, which are the 4,000 location of lampposts. Then we're starting to set up our automated joint design by selecting the fiber backhaul design option. So this option will allow to automatically request multiple exchanges between Siradel and Comsof tools to come up with a cost-efficient small cell network backhaul with fiber. Then the user sets the objective that needs to be achieved for the wireless coverage. As described earlier, in this use case, we have expressed the coverage objective to cover 80% of the area with a received power threshold. Once the computation starts, the propagation simulation of the different candidates is generated and triggers the start of Comsof application. Both tools are exchanging data to come up with the optimal solution. Once the computation is done, a report is generated providing information about the number of small cells that have been selected, as well as statistics about the coverage area, like the percentage of pixels covered with a certain modulation in the study area. At the end of the report, the user can open a bills of materials spreadsheet that's been generated by Comsof tool, and this spreadsheet provides a comprehensive description of the cost associated to the deployment of the fiber network. Going back to the interface, in addition of the report, results have also been imported, like the location of the candidates that have been selected for the small cell location, as well as the layout of the fiber network to provide backward connectivity to the small cells. The user can also visualize the coverage maps that has been simulated for each of the small cell location for different metrics. So this video ends the presentation of the first use case, and I will now hand it over to Kevin for the presentation of the second use case.
Okay. So the second use case that we're going to look at is the savings that can be achieved in converged network planning. The purpose of this exercise is to compare the cost of building a standalone fiber to the home network and a standalone fiber to the 5G network with the cost of building a converged network that covers both for fiber to the home and 5G antennas. For this use case, we looked at different areas around the world and ultimately determined that we could group them into 3 different population densities: high density or urban, medium density or suburban, and low density or rural. In addition to designing and comparing the cost of the 3 networks for each area, we also utilized our integrated solution to compare the cost of designing the networks with 3 different antenna or small cell site densities. There's a lot of design comparison for a given area, which is why having automated tools can be so helpful. Quickly, before looking at the results, we have a graphic here that overlays a separate fiber to the home design with a fiber for 5G design. It is quite evident by looking at this, we can see some areas where we'll be able to save on material, but also the labor costs. If we can see where this fiber cable for the 5G, which is a bit thicker, overlays the fiber for the fiber to the home, we realize that 1, if it's underground, we won't have to dig twice, but 2, irregardless, things like pulling cable, getting right-of-way or make-ready, all of that can be done at the same time, which will be a significant cost savings. So now the results. Looking at them, we have some pretty compelling numbers. So what you see on the top left there is how it's actually broken down. We have the cost for building fiber to the home network, the cost for the fiber to the 5G, and when we stack both of those compared to the cost to build the fiber for both of those networks at the same time, we can see it's quite more economical to build it at the same time. So the 2 scenarios which we'll see most often is in a high density area having a high density of small cells, and in a low density area having a low density of small cells. So in the high density area, it would actually only be 5.6% extra investment to make fiber to the home 5G ready. And this is in terms of the fiber backhaul. If we look at the low density area, it would actually only be a 1.9% extra investment to make the fiber to the home 5G ready. So when we see that, that's a very small percentage of the overall cost to make sure we have the fiber ready for our 5G deployment. Now remember, these numbers are based on the labor and material costs that we use, but again, with such software, you can implement your unit rates and see what it would mean for you. So with our second use case done, what can we take away from what we saw here today? Well, obviously, we have discussed 5G networks and their need for fiber to achieve their performance requirements. We looked at the traditional wireless network design workflow and how it does not achieve the savings that are possible with an integrated wireless and wireline approach. This led to the introduction of our joint integrated solution in our 2 use cases. The first and perhaps most compelling was where Sylvain showed us how our joint automated approach can achieve savings compared to a sequential design. And the second use case showed us how we can plan for a converged network when deploying fiber to the home, which will provide significant savings for our 5G fiber deployment. Both of these were shown as just examples of the significant cost savings that can be achieved by utilizing this joint integrated solution to designing 5G networks. This is just the tip of the iceberg with regards to the capabilities of this joint solution, and there's a lot more that's coming on the way. I'll pass it over to Jolie now.
Thank you, Kevin. We would like to remind everyone to please take the survey that you will receive at the end of the webinar. I will now open the floor to the audience to answer any questions you may have. All right, so for our first question, how long does it take for a calculation to run?
I'll take this one. So in the video we have seen we have accelerated the process for the purpose of this webinar. The length of a computation will depend on the density of cells, of candidates, on the size of the area and the complexity of the environment. To give some figure, the study area for use case 1 that we have presented here took a simulation time under an hour to achieve the results that we have presented.
All right. Our next question, what kind of input data do I need? And how do I get the input data for this calculation?
Well, that's a good question. So in order to do the wireless modeling, it's really pertinent to have some 3D data because especially now with millimeter wave, you'll need to look at things like line of sight and all of that. So definitely 3D building data. And then for the fiber, it's not as important. So just things like your streets, and if you're going to go to somewhere where you have existing assets, any of your existing fiber, handholds, manholes, those sorts of things.
All right. Next question, am I able to design for different frequencies and coverage scenarios?
Yes, definitely. The use case we have presented here was focusing on millimeter wave, which is a major new frequency band for 5G deployments, but the tools support both sub-6 and millimeter wave. Extensive deployments have been done in the sub-6 frequencies, 2.5, 3.5, that can be simulated, and the same approach can be applied here.
And can you model different fiber architectures like GPON versus point-to-point for the fiber backhaul?
Yeah, that's another good question. So we didn't get too into it here, but we have what I had mentioned, which is what we call our design rules or our architecture for the fiber side. So we can do passive or active. I guess with NGPON2 that there's some talks of using passive for 5G fixed wireless, but definitely we can do point-to-point. It's just depending on how you want to design your network.
Do we need to tune the propagation model for wireless coverage?
So that's a very good question. So we are providing the solution with a propagation model that comes with pre-calibrated model. We have been developing this propagation model for more than 20 years now with extensive usage in the sub-6 frequency band, and we have also recent evaluation in the millimeter wave band showing good match between the prediction and simulation. So the tool comes with pre-calibrated model. But the user has also the capability to tune his model within the platform.
All right, now we have a question about the formats available to export files, like fiber, coverage, or locations.
The formats that we're supporting are traditional formats used in the GIS industry, shapefile, mapinfo file that will allow to use those formats across like multiple platforms without any proprietary formats.
Mm-hmm. Yeah, GeoJSON we support, geodatabase, all of that.
What do you take into account for SilverWorks cost calculation?
Yeah, that's a good question. Because that really will drive your use case. So it can be as much or as little as you want. It really depends on how good of data you have, and obviously that's what's going to really drive your costs. So you could do things like trenching, horizontal directional drilling, boring, and then on the aerial side, things like your putting in new poles, using existing poles, your make-ready, overlashing, all of that. And then also on the civil side, the actual components of the network, so your handholds, manholes, ducts, microducts, fiber cables, the actual equipment, all of that in terms of the labor and material costs.
Can this solution be used for indoor or in-building planning?
So the solution we're presenting here today focusing on outdoor deployments, so is at this stage not available for indoor or in-building planning.
All right. Well, we received a lot of great questions, so that's great. But sorry we couldn't get to all of them, but we'll be sure to reach out and get back to you. And please don't hesitate to contact us with any questions about how we can integrate Comsof Fiber and Siradel into your project. Thank you for tuning in, and to our American attendees, happy Thanksgiving.